Good. So let me introduce the last speaker for today, Kjall, who is a PhD student with kjall at Berkeley, and he will be talking about EA symmetries and easing chains. Okay, yeah.
Thank you. So I will talk about some work we've done recently that I've done together with a postdoc, or I guess a previous postdoc in our group, who's now at Taipei, Taiwan, and he's soon going to a bit more permanent position at the Max Planck Institute in Dresden, and my advisor, Bill Moore. So the talk is in advanced stage of EA symmetry in quantum-like chains. And this is motivated by a recent experiment done that was the first experimental evidence of EA symmetry in physics. And done by Correa and colleagues in Oxford. And the paper is called Quantum Criticality in an Ising Chain, and the experimental evidence for emerging EA symmetry. And it's based on some very old theoretical work that was derived in a two-dimensional classical Ising model by Samolotchikov back in the 80s. So, but actually, I guess our motivation for this project was slightly different when compared to the usual motivation. There's this numerical method called time evolving block decimation that Frank, the postdoc, has been working a lot with, and he's very good at that. So it's a method where you can simulate 1D quantum systems very well, and it's based on the matrix product state representation, and it's very related to DMRG. It's like a descendant of the DMRG algorithm. Nowadays it's basically the same method. And you can get the ground states very, very well by time evolution in imaginary time. But it's probably more like the real time evolution that's been more interesting recently. And this is something Frank and I wanted to do. We wanted to take his code and extend it a bit to be able to simulate, to see how long times we can simulate, and see if we could be able to calculate the dynamical structure function by taking the Fourier transform of the relation function in space and time. So this is a computationally pretty hard problem. So we have to implement various different things. We can't calculate the correlation function every time since it's very computationally demanding. So we only did it 10 times that we interpolated value between. We also use the so-called light cone spread of entanglement. It's spread out. If we have the ground state, they want to do a local perturbation from that, the entanglement spread out. So we don't we can extend our system as time goes on. And also we use linear prediction to get longer times. So we basically wanted to find some interesting new physics where we could sort of apply this method to. So that was kind of how we choose this. So let me now start to talk a little bit about. Yeah. So my plan is actually to skip all the technical talk about the numerics to the end if I have any time left, because I would prefer to talk about the physics if that is okay for everyone. So let me start with a very basic quantum Ising chain, where we have if this J is positive, it favors the ferromagnetic state. So it's either all spins up or all spins down. And if we increase the transverse field past, we have a critical point there, we get into a ferromagnetic state that all spins like this. And in this notation, where I use the spin operators, the critical point is at J hat. So, as I mentioned before, we were mostly interested in the dynamical structure function and the excitation spectrum. So the elementary excitation in this system is in the ferromagnetic phase. It's like a domain wall or a kink, as I would call it from now on. And it's a spin flip in the ferromagnetic phase like this. And the excitation gap closes at the critical point. But experimentally, we can't really create like just one domain wall like this. Since if we are like in the ground state in the ferromagnetic phase, if we excite the system, we will flip one spin, and that is like to create two domain wall, one on each side of the flipped spin. And since we have like this twofold degeneracy of a ferromagnetic state, these two domain walls are like free to move. In this case, it doesn't add any energy, since all spins down has the same energy as all spins up. So these two domain walls are completely free to move. Okay, yeah, and if you have any question, please interrupt me anytime. So, but to get these bound states, we need to confine these domain walls somehow. And so we start to look on like a long chain.
Can I ask you a question?
Yeah.
First, so
Yeah.
what are the other elements? So basically, you create something which is very non-equilibrium. You flip the speed.
Yeah.
Right, and basically these. Do you create something else in addition to those guys, or those guys are just the only excitations you have?
Yeah. So it's experimental. I guess they do it by neutron scattering. There's like a neutron coming in here, and it interacts with like one spin on one atomic site and flips it.
And you just and you will observe just two-wave packets propagating away from each other. This
Yeah.
is your simulation.
Yeah. Yeah. I guess. Yeah. They are.
And
they are
nothing
free to
else.
move.
And nothing else.
They are free to move. Yeah. So. Yeah. I think. Yeah. I think they probably don't just can move away from each other. They can probably move a bit back and forth. Also, or at least they are not like they can have different move away from different velocities and so on. We get like a whole continuum in the excitation spectra. So a little bit more about that later. So if we apply like a longitudinal field to a transverse Ising chain, this will break the twofold degeneracy of the ferromagnetic phase, since it favors, like, for example, all spins up, if this is a positive constant. And it will also open up a gap. It's not a gapless system anymore. And it will move this, since this field favors a ferromagnetic compared to a paramagnetic, it will move the minimum gap to higher, here to be transverse field. And most important, the thing that we are mostly concerned about is that it will confine the kinks into band states. And I'll talk more about that.
Why are you calling this system gapless? I guess it's gapless only at the critical point.
Yeah, it's gapless at the critical point, right. But if we apply a longitudinal field, we move away from the critical point, so it's not gapless anywhere. So there's actually two ways we can get this confinement, or at least two ways we can get confinement into bound states. We can have, so if we have these two domain walls I talked about before, where like they start just with one chain, but if this one chain is coupled to like another ferromagnetic chain with ferromagnetic interactions as well. So for every spin we flip, if this coupling is weak, like we get like a positive energy contribution for every flip spin here. So we'll get, as the domain walls moves further apart, we'll get like a linear confining potential, or like a absolute value of x confining potential. And the same thing will happen instead of if we have this ferromagnetic chain coupling, if we have a longitudinal field that favors spin up and gives a positive energy contribution to the spin downs. So the kinks will now be confined 2 and 2 into bound states, and it will split up the excitation continuum. So there is some analytical solutions to this in certain limits. At low transverse field, a small bound state momentum, this is the thing I talked about. We have this linear confining potential, and that can be solved by the one-dimensional Schrödinger equation. Yeah, with the confining potential. And the energy levels of that are the zeros of the area function.
exactly mean by low transverse field? I mean, I thought you were very close to the critical point. Does that mean that
Yes.
transverse field deviates very little from the
Yeah,
critical
so right now we are here.
Oh.
And I will talk later about
Oh.
this point. Yeah. Or I guess, yeah. So this was just to be able to explain, because there is not like a very intuitive way to understand it at the critical point. So here, the other analytical solution is like here, this critical point. So before we had this longitudinal field, we have this gapless here, and we open up a gap at a critical point. And this was solved back in the 80s, as I said. And instead of having like the area, the series of area functions that basically have like infinitely many bound states, we now have only 8 bound states. And I guess there can also be, combinations of them, of course. And the mass ratios, I mean, this is a very small gap, which goes to 0 with as the longitudinal field goes to 0. But the mass ratios, at least, are given by these values. And for example, here, the mass ratio between the second and first bound state is this golden ratio.
This is now close to quantum critical point.
Exactly. So now we are close to quantum critical point. Yes,
So the
like
area
curve
type
with-
spectrum gives way to E8 symmetric spectrum.
Yeah, as we increase the transverse field from roughly 0 to the critical field. So, as I said, we can also have like several bound states, as you saw here. The mass here, the third mass is roughly twice the mass of M1. So we'll get a continuum here of bound state pairs, 2 and 1, and so on. So, and how do we get these? When the kinks get sufficiently far apart in like one bound state, it can be like energetically favorable to like flip another spin between them, and thereby creating 2 more kinks. And those kinks will like form with one of the older kinks each, form like 2 bound states that basically are like independent and create that continuum as well. And I also forgot to mention that like the spectral weights of these peaks goes down very fast. So it's expected to be very hard to like observe more than like the 2 degree first or something like that. Yeah, so to summarize a bit, as you said, we have here at low transverse field and low longitudinal field, we have an analytical solution, basically with all the energy levels being very close to energy J, and infinitely many energy levels here. And here I have here we have done a simulation between the whole dynamical structure function as a function of momenta and energy here. So the bound state masses I normally talk about is the energy at 0 momentum. So as we go from here, where we have infinitely many energy bound states, they decrease and decrease, and here close to this critical point with very weak longitudinal field, we should have 8 bound states. So the goal with our work was to simulate the excitation spectra for the transverse action chain in the longitudinal field for basically whatever value of both the transverse and longitudinal field, and see if we could derive an accurate microscopic model for this cobalt niobate that they used in the experiment to investigate this symmetry. And then we could see if we could simulate the excitation spectrum of cobalt niobate close to this point and see what we get. See how well it matches with what it should be for the transverse Ising chain, how well cobalt niobate agrees with the transverse Ising chain in the longitudinal field. So what I mostly will show you are like these cross sections at 0 momentum, where I have like the bound states. So we have here I have energy and the intensity up here. So this is this is just, I will start just now with the Ising chain. So I use these values since they are related to the continuum rate I will talk about later. So we are at critical transverse field and very weak longitudinal field here. So here we can see like up to 5 bound state masses easily, and we can also see like 2 bound state masses there that form this continuum M1 plus M1, M1 plus M2 as well. So this was like, yeah, a lot better than we expected actually to be able to see. And here is the same plot, but for like higher longitudinal field, and we can still see like all the same features. The difference is that the bound states are of course spaced further apart as we increase the longitudinal field, and also the weight of the continuum decreases quite a lot as the longitudinal field increases. So we continue here with Ising chain, and now we plot for more longitudinal field. So we go along this line, like far away from this critical region, and go as close in as we can with the simulation. So here I plot the energy of the bound states as a function of the longitudinal field going in here. And I also have like this asymptotic expansion, like this analytical work done by Fateh in the 90s. That should be exact when we go into like zero longitudinal field. And we see we have like surprisingly good agreement. At least I was surprised like how far out it agrees well to like high longitudinal field, which is like on the order of these fields up here. And here I plot these like mass ratios given by Sinological's original paper, also as a function of the longitudinal field. And it approaches the analytical calculated value as well, as the longitudinal field goes to zero. I guess we have some small fluctuations here due to like when the bound state gets really close, we don't really have like a good enough energy resolution in our simulation. And here is also another simulations we have done as a function of the transverse field instead, basically like along this line here. And we can see now, as I said before, that the gap minimum has been moved pretty far away from like a very weak longitudinal field. It moves the gap minimum very far away from the critical transverse field. That is this this line here. And here again, I take all these mass ratios and divide by M1 and have all these mass ratios. And they basically go like straight lines, as you can see, past the analytical calculated values at the critical field. And also like that this gap minimum has moved very far away, at least with previous theoretical work done as well. Very well. Okay, so let's now move on to the material that Korea used in their experiment, this cobalt niobate. And it's a material that has like Ising spins on every cobalt 2+ ion, and it consists of like weakly coupled zigzag ferromagnetic chains. So the cobalt ions are like in here in the center. And it's like weakly coupled chains, so the 3D model of a material is we have like all the chains here on these red dots going out of the plane, and perpendicular to the chains we have like this basically triangular pattern, but there's a slight difference. It's actually slightly longer here. This coupling is slightly longer, J1 and J2, I think. At least that's what they say in other work done on the system. And it has like a ferromagnetic structure in this plane, at least for all the transverse field we are interested in this work, all the way up past the critical field. And this is some other previous analytical work that shows that if we have like a magnetic ordered material at low temperature, we can well approximate this ferromagnetic weak interchain interaction with like a longitudinal field. So, but we need to add, to have like an accurate model of cobalt niobate, it's not enough to just have like a transverse quantumizing chain with this longitudinal field that models the interchain coupling. We need to add more. I said it's like an icing, but it's just like a strong easy axis, so it would still be like a weak XX term present in the model. And also we have these zigzag chain, so the next nearest neighbor interaction in the chains is probably important as well. So the Hamiltonian we use to model cobalt niobate looks like this. We have this XX term and the next nearest icing term here. And all the previous terms I had in my icing chain.
But you're saying that you don't have to worry about correlations between chains.
Right.
You're just putting them in as an effective.
Yes. Yeah. So this term, as long as I'm like in the magnetic order material at low temperature, this term should describe a ferromagnetic interaction between the chains as well. So here is the neutron scattering data from Colbia that shows this at low transverse field. And so we basically try to get the dynamic structure function to look as close to this as we could with the Hamiltonian I showed you on the previous slide. So, and by fitting parameter values, as you can see here, we got this. So unfortunately they are a little bit, here is momentum 0 and experimental data, and here is the Berlin boundary. So hopefully you can see that it fits very well. It's not, or at least like it looks as good as can be expected from these numbers, or from these graphs. And what else? Yeah, so I should say, so these values we will use apart from the transverse field. These are the values we will use when we go closer to the critical point, and we will just vary the transverse field. But to be really sure that these were the right values, of course, we took like all these cross sections. I'm talking about it again, especially at K0, but also at other points. So here is, for example, the cross section at K0, and here we can see like the first 5 bound states, which should be close to the area functions, of course. And you can see the pluses here are the energy for our 5 first, and the circles are from the experiments, and the crosses are from like the first order model they developed in that paper, and that was solved by Lukowicz later. So we have like as good agreement as we can get, I guess, from this experimental data in these parameters. So I guess the new thing that comes up here, the big new difference compared to the transverse icing chain in the longitudinal field, is that we have like this kinetic bound state that is very prominent up here for like high momentum. And this is like the bound state that is instead, it's not stabilized anymore by the potential energy at when the total momentum on the 2 kinks is low. So here we have like high momentum. So it's stabilized instead by the kinks moving together. And this is a short range interaction, and it's basically this new XX term that gives energy gain in hopping. So if we have, let's see here. So if we have 2 domain walls really close to each other, like this, we have the domain walls here. This term can just move the spin one side to the right or one side to the left. But if we have more spins further apart between the domain walls, this term will not do that. It will flip one spin. Let's see here. So it will flip this spin, and it will flip this spin. So it will have like create two new domain walls, which is very like not. It adds a lot of extra energy, so it's not that favorable to the system. So it really favors just hopping when the domain walls are close to each other this turn. And this will stabilize the kinetic bound state. So now we take this Hamiltonian with the values I showed you before and increase the transverse field close to the front critical point. And we get this dynamic structure function like this. And we can see like the flattening of the kinetic bound states. But we can still see like all like the first 5 bound states and 2 bound states pairs can easily be distinguished. And we have still, yeah, the relative density of the state seems to be fairly unaltered with adding of these extra terms to control my obey. So again, we do the plotting as a function of the transverse field past the corner critical point for, I guess it should be like slightly above since we have like a longitudinal field. And if you remember the previous graphs, they look exactly the same, at least at the first glance. We have these straight lines of the mass ratios going through the analytical calculated values at the critical field. The only thing is actually that both axes are basically rescaled by 10%. The critical point has been moved down to 0.814 instead of 0.915 before, and the same with the minimum gap is now at 0.99 instead of 1.1 MB. And the same thing is that the gap has decreased a little bit from 0.33 to this value. But apart from that, it looks exactly the same, more or less. Yeah.
Question.
Yes.
If you already said that, then I missed it. But so you think 2 and 1 plus particle can have any energy because they can move.
Yes.
Move with opposite moments or something. But M1 plus M2 has 1 sharp energy.
Yes. Yeah, here it looks pretty sharp. So M1 plus M1, where it starts overlap here with M3. So this is something I'm not actually entirely sure about. Maybe someone knows the answer to this, but I don't know if you continue, so like have like a peak at the start of it, or if for some reason it seems like if the M1 plus M2 is more isn't really a continuum. I'm not entirely sure. That's a good question.
If there was a peak, it would be hidden by the M3.
Yeah, so M1, if M1 plus M1 had a peak, yeah, it would be part of M3 peak. We are like so close to the so we can't resolve it with our energy resolution.
Why do the peaks have a lift? Is that from the resolution, or is there actually a lift there?
Yeah, so that is from our energy resolution. So yeah, so these should be like delta function if we can simulate to like infinite time. Yeah. Okay. And this slide I talked about before. So here's some comparison with the experimental data we have. As I said before, it's really hard to distinguish too many peaks, especially close to the critical point. So far we have only been able to get the M1 peak all the way and the M2 peak roughly to the critical point, and not more than that. So at least now we can get more by numerical simulation, but it agrees fairly well, at least with first M1, M2 to here. I guess the biggest difference is that they have a bigger gap than we have at 0.36, 0.3.
But you can play with the value of this gap, can't you, in your calculation?
Yeah, yeah. So I mean, the values we used, we started out to like fit to this value at low transverse field, where we had more data.
Yes.
And here, close to the corner critical point, the experimentalists don't have. I mean, this is not much data really to fit to, so we didn't really want to fit it here. But something might happen when we go from like, I don't know, there might be something else that we're not including in our model.
So how does the simulation x-axis and the experimental data x-axis related?
Yes, so they are, yeah, so the way, yeah, so this is, I guess, something I forgot to mention. So the experiments, I guess the new thing is that they were able to get this material to like a very low temperature and are able to like apply a very high magnetic field, which is this transverse field, applied to transverse field.
Yeah, so my question is like, is it just a matter of scaling or is there some offset when you go from this, when you try to relate the
magnetic field to the
experiment
transverse field?
Yeah.
Yeah, as far as I know, they are directly related. But
I mean, are they proportional or is that?
yeah, as far as I know, they are proportional. Yeah.
Okay.
Yeah.
It's not just linear; it's proportional. Okay.
Yeah. So I guess one thing they probably, I think, they got wrong in the experimental paper was that they didn't say that the mass ratios should follow like straight lines and pass the analytical values at the critical field. So the critical field is like here somewhere, but they said that the mass ratios should bend and approach the analytical values at the minimum gap. So at the minimum gap, like here, not at the critical field. But apart from that, I mean, I think the critical field is like roughly here, and I think to this experimental data you can as well like fit the straight line that goes through this line here.
Why didn't they take a code about that?
Yeah, so they were not able to like to resolve M2 for like higher fields than this. This is how far they got. I mean, even like these points are like very, I guess, pretty big error. These points, they are. Okay, so the conclusions are that we're able to find like a good macroscopic model that we can simulate of cobalt niobium, and that the mass ratios, as I said, will follow straight lines through the analytical values at the critical field strength. And improved experiments should be like on this material. This material describes the Quaramycin chain longitudinal field very well, so they should be as likely to find the higher bound states as if they were doing the experiments on this pure Quaramycin chain longitudinal field. Okay, so any questions about that? Yeah.
Yeah, Fred mentioned what exactly is EH symmetry?
Yeah. So unfortunately, this is something I should read up to. I've tried a bit, but I still don't fully understand.
It's an exceptional group of rank 8. So it's one of the complex, complicated finite groups with very beautiful structure.
So, but then does that only occur exactly at the critical point?
I think so.
So
Yeah.
once you have finite field, then it's actually
Doesn't have exact.
So it's not exact.
Yeah. So it's solid by quantum field theory, and you get this symmetry, which I guess was a bit surprising at the time. You have this Ising model, and then you have like a hidden E8 symmetry in it. But
It's a theory of the world, by the way. There's a fellow who has E8 and related larger exceptional groups theory of grand unifying all interactions.
Yeah, I guess it contains a lot of subgroups of like the other lower exceptional groups and also like lower usual groups.
So are you proposing that this experimental system can be understood as some almost E8 symmetric?
Yeah, so I guess
slightly
what we're
broken away?
saying is that this material, at least, I mean, it's of course not like a perfect quantumizing chain, but you should definitely see things from this E8 symmetry by doing experiments on this material. And I mean, the things that they see is like these bound states, mass ratios.
So I have a question. When you don't have the longitudinal field, the domain walls in the Ising chain have these zero energy modes, right? Do you still have that in the longitudinal field? Probably not. Okay. There are no zero energy fermionic zero modes.
No, I don't think so.
Because the longitudinal field looks very non-local in terms of fermions when you do the Jordan-Wigner transformation.
Yeah, I mean, it's not. You can't solve it by that transformation.
So,
Yeah.
I might not remember this correctly, but you showed one of the graph you had the experimental data in your result, and you also have the theory from that experimental paper.
Oh yeah.
That was actually a more general question. It looks like your theoretical result extremely similar to even the theoretical result that produced an experimental paper. I'm just curious, what was the method you used there, or why is?
Yes.
Do you predict something that they didn't, or?
Yes. So they have like the first order model, the perturbation in like the transverse field. So let's see here. I have some graph here. Yeah. So they have like a first order model, the perturbation in the transverse field from here that describes the experiment well, like in this region. But they can't use that region to go to like higher transverse fields.
Okay. So you have data that's past there.
Yeah. I mean, we can simulate like anywhere we want in the phase diagram. Yeah. So I guess that was the physics. I have some slides about this numerical methods we use in TBD for matrix product states, but I guess it's getting fairly late, so maybe for those of you who are interested can, I don't know, talk to me, or if some of you still want to listen for another 15 minutes, probably not, so.
Let's thank the speaker.
Yeah.